Hey guys, welcome to another video. Today we're going to be covering the kinetic theory of matter, which is one of the first things that you need to know if you're studying igcse chemistry. So without further ado, let's begin. So the kinetic theory of matter states that matter is composed of a large number of small particles that are in constant motion. And so this is otherwise known as the kinetic molecular theory of matter or the kinetic theory of gases. So there are three states of matter. You've got the solids, the liquids, and the gases, right? In a solid, the particles are held close by, they're always in fixed positions, and they are always vibrating on its spot. As you start to give the solid more and more energy, the individual particles will gain that energy and vibrate faster and faster. As that happens, they start to gain separation from one another because they break free from the attractive forces that they have for one another. So therefore, as they separate, the particles will eventually become able to slide past other particles and sort of move around, and in that instance we start to call it a liquid. If you start to give it more and more energy, then they will separate even more as they break free further from the attractive bonds, and so the particles have a huge separation in gases. Of course, you've got a name for everything. From a solid to a liquid, you call that melting, and a liquid to a gas, you call that either boiling or evaporation. Mainly boiling. Evaporation is slightly different, but we will cover that in the future. The gas going to a liquid, is condensation, and a liquid to a solid is freezing. Sometimes you can skip steps. You can go straight from a gas to a solid. We call that deposition. You can go from a solid straight to a gas, and that's sublimation. So the Brownian motion basically demonstrates the random movement of particles, right? So a scientist was basically taking a look at a pollen grain, and he found that the pollen grain was inside water, floating on top of water basically, and he found that at a microscopic level the pollen grain was constantly moving in a random fashion, right? So this sort of depicts the pathway of the pollen grain. You can see that it's quite random. And it's always moving. So what's really happening is that the pollen grain itself is getting bombarded at a random, pace by the water molecules or the water particles, right? And so that would support the kinetic theory, by which the particles are always in constant motion, but and the Brownian motion suggests that it's always in random motion as well, because the pollen grain itself was moving randomly due to the random bombardment of the by the water particles. Okay, so that's a fairly short video. I hope that helped. Please check out my new website, www.freeexamacademy.com. It's by no means complete at the moment. It only has biology, so if you guys are studying biology, it has a couple of notes there for that, so please check it out. Otherwise, please like, share, and subscribe, and comment below if there are any sort of topics that you want me to cover, whether it's physics, chemistry, or biology. Okay, so thank you very much, and I'll see you in the next video. Hey, what's up guys? Welcome to another revision video. Today we're going to be covering the experimental techniques in the igcse chemistry syllabus. So this is a quick overview. We're only going to be looking at the idea of paper chromatography and fractional distillation, because that's probably the most hardest parts within this topic. If you want other comprehensive notes in other areas, please visit www.freeexamacademy.com. I have written down some pretty comprehensive notes for this the entire topic basically, but in this video we're just looking at paper chromatography and fractional distillation. Okay, so paper chromatography is basically a separation technique that is used to separate and identify the components in a mixture. So let's take an example, right? Let's just say that our sample has a mixture of three substances. Okay, so we're basically going to get a sample of that mixture, and we're just going to blot it on what we call a chromatography paper. And it's important to draw a line where you sampled it, because that's important later on, and you'll see why, and that's called the origin line. So what's going to happen then is we set it up in this sort of setting here, whereby you sort of hang the chromatography paper down where the ends are just touching a solvent that can be propanone or water, but let's just take water in this example here. So you've got your origin line here, you've got your little sample, and you sort of just leave it to be for a certain prolonged period of time. And so what happens is that the solvent will actually gradually rise up in the paper, and in doing so it will meet the sample, and the sample will actually dissolve in the solvent, right? But the idea is that certain substances have different solubilities in the solvent, right? So we took that this little sample has 3 different substances inside this mixture. So those 3 different substances will have different solubilities in this solvent. What that means is, as the solvent travels up, the substances or the mixture will actually travel up as well, but some substances inside the mixture will actually travel slower than others. So eventually you reach an end point, and different substances would have made it up at different points because of the speed differences in which they go up with the solvent. So you might get something like this at the very end of the experiment. So the water level has obviously rose up to the top here, and the 3 substances has actually separated out, and obviously the yellow one traveled the slowest, the blue one has traveled the fastest. And so once you get these results, what's really important is how are you going to analyze it? Well, first of all, given that you've got 3 spots here that have originated from the sample, you can see immediately that it is a mixture, and we've already established that. So this little sample here contains 3 different substances, so therefore it's impure. If you take a look here, what's really important is that you take the solvent distance. Okay, so that is how much the solvent traveled upwards, and you also have to measure the how much the different spots have traveled up. And this is why the initial origin line is important, because that's where you start to measure everything from. That's our reference line. So what you do now is calculate the RF value of each of these different substances, right? So the RF value is the distance traveled by the spot, okay, so A, B, or C, divided by the distance traveled by the solvent. So let's just calculate each and every one of those. For the yellow spot, okay, so it's traveled from 0 to 2.5, so you divide 2.5 by 6.5, which is what how much the water traveled, and you get a value of 0.38. You do that for the purple and the blue, and you get the values that you see here. This is really important because each substance has a unique RF value, and in an examination setting, they will give you a little chart that states, this substance has an RF value of this. So, for example, in this example, we get an RF value of 0.92 for the blue spot. If you look at the reference table, it will say something like 0.92 RF value is called XYZ. So you just you derive it from that, but they'll always give you the reference chart. Okay, so if we established that it was a mixture because it had more than 1 different separations. If it was a pure substance and you did paper chromatography, you'd only really get 1 spot as a result. So the other important topic in this part of the syllabus is fractional distillation, which is a technique that is used to separate a mixture of liquids, and the liquids have to be miscible, right? So the idea behind fractional distillation is that it uses the fact that different liquids within the mixture will have different boiling points. So let's take a look at this setting here. You've got the flask that contains, in this example, we're going to be using a mixture of liquid A with a boiling point of 50 degrees and a liquid B with a boiling point of 100 degrees. And what we're going to do is heat this flask. And as the flask gets heated, right, obviously all of the equipment is going to get heated as well. What's really important is that the bottom part, so as you heat the flask, it's going to heat the column as well, right, the fractionating column. And what's really important is that there's a temperature gradient that will form in the fractionating column. Because you're heating the equipment from down below in the flask, the bottom part of the fractionating column is always going to be hotter than the top part. So let's imagine that you start to heat this up with a Bunsen burner, and you reach a temperature of 50 degrees here in this flask. What do you think what's going to happen then? Well, once it's reached 50 degrees, then liquid A is going to start to boil and therefore vaporize. So the vapor is going to start to go up, right? But the bottom part of the fraction might have, a temperature of 50 degrees. But as I said, there's a temperature gradient. So the bottom part is always going to be hotter than the top. So as you get to the mid-range here, it might only be 40 degrees. So the vapor will start to rise and rise, but as soon as it hits this mid portion that's only 40 degrees, then the gas it's not gonna go up further, it's gonna just sort of condense back down into the flask. Okay, so eventually the whole column is going to get hotter and hotter, and as soon as the very top reaches 50 degrees, then the vapor can actually make it all the way up and into the condenser, whereby it cools it and it condenses the liquid into the flask on the right hand side here. But the main point is that the gas can only, the vapor of liquid A can only go up as far as the temperature of the column lets it to go. So if it's not 50 degrees up top, then liquid A will not be able to make it all the way up top, okay? But eventually it will as the column heats up. And so, as soon as all of liquid A has been condensed and liquefied, you replace that flask and you replace it with an empty one, and as soon as the column starts to heat up and makes its way all the way to 100 degrees, then liquid B will start to boil up, and the same thing will happen. It's just gonna, go up and up until the top part is 100 degrees, and in which case it can sort of go down this path here and get condensed by the condenser and again liquefy into the flask. Okay, so that is how fractional distillation works. So thank you for watching, guys. Please visit the website www.freeexamacademy.com because we haven't gone through everything, but in this site here I have gone and made some pretty comprehensive notes for the entire syllabus for this specific topic. So please just go into the site and check it out. I will put a link in the description box below. Otherwise, please like, share, and subscribe, and I'll see you in the next video. Hey guys, welcome to another video. Today we're going to be covering the topic of atomic structure in the igcse chemistry syllabus, and this is really important because it really builds the foundation of chemistry. So if you don't understand this, then you won't really understand anything else in the whole course. So this is really important. So without further ado, let's begin. So an atom is defined as the smallest particle of a chemical element, and a chemical element is basically a substance that is composed of just a single type of atom. For the sake of simplicity, let's take a look at the fact that you build a big yellow Lego wall simply just using these yellow Lego block units. Because this whole wall was built with just this yellow unit, this represents an element and this represents a single atom. If you had, of course, you've got different types of atoms. You could have green blocks, you could have blue blocks, and if you make a blue wall from just blue blocks, then that would be a different element from this one. Okay, so that's fairly simple. So the element carbon, for example, is only made of carbon atoms, and the element oxygen would only be made of oxygen atoms, and so forth. You do get the gist. So the structure of an atom is actually made of three subatomic particles. You've got the neutrons, the protons, and the electrons. Really important distinctions between these is, first of all, the charge. The charge of a proton is a positive one. The charge of an electron is a negative one. Neutrons do not have any charge at all. Secondly, the weight is also quite important. The weight of a protein is, given that it's relative to each other, just 1 unit. Neutrons also weigh 1 unit, and electrons weigh nothing at all. Okay, so this table here to the right summarizes this. Just be aware that this is the exact relative mass, 1 in 1840, but for the sake of your course, this is basically negligible, so you can say that electrons have 0 weight. Now, so the protons and the neutrons are located in the nucleus, which is the central part of the atom here, and the electrons are always in orbit of the nucleus, and they sort of lie in what we call shells, which are represented as ring-like structures that we draw around the nucleus. So let's take a look at that in a bit more detail. But before that, there's a couple of things that we need to go through. The number of protons is defined by the proton number or the atomic number, right? And in an atom, the number of protons will always equal the number of electrons, and that's really important. And that's the reason why atoms never have any charge, because the number of the charge from the protons will always balance out the charge from the electrons, making it a resultant charge of 0 always. If you have an imbalance in the number of protons and electrons, then it will have a charge, but at that point we don't call it an atom anymore, we call it an ion. So that's quite important, and we'll look at that in a bit more detail when we look at ionic bonding and things like that, right? The other thing is that the number of protons and the number of neutrons, when you add that together, we call that the mass number, because again, the mass is really only defined by protons and neutrons, because as we said before, electrons have 0 mass. Okay, so this is quite important because this is what the periodic table will tell us. So let's take a look at the electron arrangement just for a second. I've said that electrons are held inside these shells, and we sort of draw that as rings around the nucleus. So you've got the nucleus right in the middle here, and you've got the shells that are surrounding it. It's important to understand that the very first inner shell, which is closest to the nucleus, has a maximum capacity of 2 electrons. So you can't have any more than 2 electrons in the first shell. In the next 2 shells, however, you can have a maximum of up to 8 in each of these. So that becomes a bit more apparently important and useful for us when we take a look at the drawing out the diagram of different atoms later on. So this is a periodic table. The periodic table basically lists out all the elements that we know of, okay? And for example, we've got hydrogen here, helium here, all sorts of things. And the information that the periodic table gives us is quite important. So let's take a look at the element oxygen, for example. Let's zoom that up. So what you have is obviously the name of the element, and you've got the chemical symbol for the element, and you've got these 2 numbers here. So the top number, or the smaller number, is what we call the proton number, and we talked about this before. It's simply the amount of protons in a single oxygen atom. And this is the mass number, and remember, mass number is a sum of protons and neutrons. So just from this example, or this information that we have here, we can actually determine the number of protons, neutrons, and electrons in a single oxygen atom. So obviously the proton number is 8 because it says so. The neutron number is 8 because the proton number plus neutron number is 16 in this case, so there must be 8 neutrons. The electron number, as we discussed before, is always equal to the proton number in an atom, so in this case it's also 8. So when we put that into a diagram, you've got the 8 protons and the 8 neutrons inside the nucleus, and in the first shell, because it can only have 2 electrons, you put the 2 electrons there, and the rest is in the most outer electrons. The really important thing is initially just to draw the rings and fill in the electrons from the most inner shell. So ignore the rest, and first initially you just fill in the electrons from the most inner shell and then go outwards. So if this was blank, you would put 2 in, and then because you have 6 electrons remaining, you would fill that in the most outer shell. So you can see here that an oxygen atom has 2 electrons in its inner shell, and its most outer shell it's got 6 electrons. So 2 short of its maximum. So this brings us to the topic of chemical reactivity. Atoms have one single goal, and that is to achieve a full outer shell of electrons. So chemical reactions basically occur because atoms want to achieve this goal. So let's take a look at our oxygen atom, and we discussed before that an oxygen atom has 6 electrons in its outer shell. This means that it is too short of having a full outer shell. Remember, because this second shell can hold up to 8 electrons. This means that oxygen can achieve its goal in wanting a full outer shell in 2 simple ways. It's either you add 2 electrons into this outer shell, or you can remove 6 electrons so that this whole shell gets removed and it basically disappears, only leaving you with this inner shell, which of course has a full shell because it's got 2 electrons in there already. Of course, if you really think about it logically, which is easier, putting 2 or removing 6? Of course, adding 2 is so much easier, and in reality, removing 6 electrons never happens. It's always adding 2 electrons, and it does that either by sharing electrons with other atoms, which is what we'll talk about in future videos like covalent bonding and things like that, or it simply just gets it by process of transfer, and that's called ionic bonding. But again, we'll cover that in a topic in future videos. Okay, so that brings us to the next topic of what about these things here, right? So to the right of the periodic table, we call these noble gases. For example, helium already has a full outer shell. It's got 2 electrons in its most outer shell, which is also its inner shell, by the way, but it's only got 1 shell. And so basically it already has what it wants. So all of these elements to the right, these are called noble gases, and all of these, every single one of them has a full outer shell to begin with. That's why these gases are inert. In other words, they're unreactive, simply because they don't need to react with anything. They've already achieved their goal, and they're pretty happy with how they are. They're very stable elements, so therefore they're unreactive. So that just strengthens the idea that atoms really want to achieve a full outer shell, and that's why reactions happen in the first place. So that's it for today, guys. Please check out my website www.freeexamacademy.com for extra notes. I am in the process of making some notes particularly for this topic, so check it out. Otherwise, please like, share and subscribe for more revision videos, and comment if you want any specific topics to be covered. So thank you guys, and I will see you in the next video. Guys, this is Cambridge in 5 minutes, and today we're going to be covering the fundamentals of chemical bonding. For free comprehensive notes, go to www.freeexamacademy.com, but without further ado, let's begin. So this is a periodic table. We took a brief look at this in the previous video, but basically it organizes all the elements that we know of in a single table. What's really important is that it organizes elements into groups, and the groups are basically columns, right? So you've got column 1, column 2, sort of ignore the middle here. You will learn about it in the future, but you don't really need to know it now. Column 3, column 4, column 5, and so on. And the columns are important, or the groups are important, because it tells you how many electrons there are in the atoms, how many outer electrons there are in the atoms within that group, right? So for example, in group 1, all of these elements here have 1 electron in its outer shell. All the atoms within group 7 have 7 electrons in its outer shell, and this is important because, as we talked about in the previous video, it tells you what an atom needs to do in order to gain a full amount of electrons, or full outer shell of electrons, because that's the goal of every single atom out there. So if for example, fluorine, it's in group 7, so therefore it has 7 electrons in its outer shell. We know that it just needs 1 extra electron to make a full outer shell. So it would rather gain 1 electron than to lose 7, because it's easier that way. Here to the left hand side, for example, lithium here, it's within group 1, so it has 1 electron in its outer shell, and all it needs to do is remove 1 electron from its outer shell to obtain a full outer shell. If you're not familiar with this, go back to my previous video, have a quick look, and come back to this one after you're familiar with the concepts. Another really important thing is that you have metals and non-metals. Metals are the blue ones here towards mainly the left hand side of the periodic table, and the yellow ones are non-metals. The main thing is that non-metals usually have more than 4 electrons in its outer shell. So non-metals tend to gain electrons in order to achieve a full outer shell and therefore atomic stability, whereas metals tend to lose electrons because they usually only have 1, 2, or 3 electrons in its outer shell. They usually remove their outer shell electrons to achieve a full outer shell. So they have, they do opposite things. Metals and non-metals do opposite things, right? So the metals in the middle here, they're technically metals and they're called transition metals, but you don't really need to worry about that at this stage. Pay more attention to the group 1 and group 2 metals, because those ones are the ones that are going to be popping up more and more often in your course. Okay, so the first thing that we're going to be looking at is the distinction between atoms and ions, right? So as I said before, metals lose electrons to obtain a full outer shell, and non-metals gain electrons to obtain a full outer shell. For example, in sodium, we have, it's in group 1, so it's got 1 electron in its outer shell. All it needs to do is lose that 1 electron to gain a full outer shell, because that outer shell simply disappears and it leaves it with 2 shells, and the outer shell now has a full set of electrons, which is 8 electrons in the shell. So when a metal loses an electron, that means it becomes a cation, right? Because it has a charge now. Remember, in an atom, the number of protons will always equal the number of electrons. Therefore, the charges always sort of cancel out. But in this case here, if the sodium atom loses 1 electron, that means that there will now be 1 extra proton, or in fact 1 less electron, and therefore there'll be more protons than electrons now. Therefore, it will have a positive charge. So a positive ion is called a cation. Oppositely, in a chlorine atom, you have 7 outer electrons. All it needs to do is gain 1 electron, and when it does so, now that you have more electrons than protons, in this case 1 extra electron than protons, it'll become a negative charge, and a negative ion is called an anion. So basically, when an atom gets charged because it loses or gains electrons, it becomes an ion. And there's 2 types of ion. There's the positive one, which is what we call a cation, and a negative ion, whereby we call it an anion. So basically, metals, because they lose electrons, they'll always become cations, and non-metals, because they usually gain electrons, when they gain electrons and you have that electron-proton imbalance, then that's an anion, and that becomes really important. But if you look at this diagram here, the fact that sodium needs to lose a single electron and a chlorine atom simply needs to gain an electron, you see a possible win-win situation happening here. So that's exactly what happens. In ionic bonding, it's basically the bonding between metals and non-metals. Metals basically donate electrons to non-metals that really need it. So both atoms will obtain a full outer shell and become ions in the process. Cations and anions are obviously, they have different charges. Cations have positive and anions have negative charges, and therefore they are attracted by strong electrostatic forces. Opposites attract. So when that happens, we call that ionic bonding. So for example, here in this case, a sodium atom will happily donate its outer shell electron to the chlorine atom, which will happily receive it. So they'll both be happy because now they have full outer shells. Sodium becomes a cation, the chloride ion becomes an anion, and because they have opposite charges, they are attracted to each other. Similarly, a magnesium can actually form ionic bonds with chlorine as well. In this case though, the magnesium atom will need to lose 2 outer electrons in order to achieve a full outer shell. So therefore, it basically donates it, 1 to each chlorine atom. So the 2 chlorine atoms will happily accept those, and so they will all bond together via ionic bonding, and in which case 1 magnesium ion will combine with 2 chlorine ions, because there's 2 chlorine atoms that had received an electron each. So the chemical formula in this case would be MgCl2, signifying that for every magnesium ion there's 2 chlorine or chloride ions. So the previous diagrams sort of, diagrammically tell you how things work, but in reality, the final structure of an ionic compound doesn't simply look like that. It looks like this, whereby ions, a lot of ions, are they form a regular structure whereby the ions alternate from positive to negative, and they form a regular structure, and that's what we call a lattice. And all these are ionic bonds. All the ions attracted to each other, held by ionic bonds, i.e. the electrostatic forces of attraction that they have because they're oppositely charged. But donating and accepting electrons is not the only way atoms can bond. So there's something called covalent bonding, whereby there's no donation or anything like that, but simply atoms share a pair of electrons, or 2 pairs or 3 pairs, right? So this is only capable. This only happens between 2 non-metallic atoms. Okay, or several non-metallic atoms. The idea is that non-metals can share electrons with other non-metals to form covalent bonds. So by sharing electrons, all atoms will obtain a full outer shell. Take a look at hydrogen here. So 2 hydrogen atoms are sort of looking around, seeing if they can obtain a full outer shell, and they realize that if they share their electrons, like so, both hydrogen atoms now have a full outer shell because they've got 2. Okay, so these 2 electrons are shared amongst the 2 atoms. Okay, so this one now has 2 and this one now has 2. And so this is a sharing of a pair of electrons, and this is what we call a single covalent bond. In water, similarly, you've got hydrogens looking to achieve a full outer shell, and you've got the oxygen. Quite simply, if all of these shared a pair of electrons like so, you can see that oxygen has 8. Okay, so that's a full outer shell. And hydrogen has 2, and that's also a full outer shell. 2 is a full 2 electrons is a full outer shell for hydrogen, because this is in its first shell, whereas oxygen, this is in its second shell, and therefore it has a capacity of 8. So therefore it needs 8 electrons to achieve a full outer shell. And you can see that everyone is happy here. You don't always share a pair of electrons, though. Sometimes you can have 2 pairs of electrons being shared, and that's called a double bond. And if you share 3 pairs of electrons, that's when we call it a triple bond. There are a lot of different examples that Cambridge wants you to understand, and I've gone through all of this in the website www.freeexamacademy.com, so please check that out. And otherwise, we will move on to the idea of intermolecular versus intramolecular forces. This is really important, right? So here, this is a group of water molecules. Okay, this is what you find in a glass of water. The solid line represents intramolecular forces. This is basically covalent bonds, right? These are extremely strong. The bonds that you form between atoms inside the molecule are really, really strong. The dashed lines, however, are intermolecular forces. This is very different. This is the forces between molecules, not between atoms. So these bonds are much weaker. Now, when we boil water, we're breaking apart not the solid lines, but we're actually breaking apart the dashed lines, and this is really important. So that's why water isn't that hard to boil, because the dashed lines, or the intermolecular forces between the bonds, are not that powerful. That brings us to the topic of macromolecules. Macromolecules, on the other hand, are giant molecules where millions of atoms are joined to one another through intramolecular bonds or covalent bonds, right? So all these atoms are bonded through covalent bonds. Okay, so diamond and graphite are both examples of macromolecules of carbon. So the atoms, because they're all joined by covalent bonds, when you try to melt a diamond, you're actually trying to not break apart the intermolecular bonds this time, because they don't have any. You're trying to break apart the covalent or the intramolecular bonds, and that's why they are extremely hard. They have really, really high melting points. It's really hard to melt these things. Okay, so you do need to understand the properties of diamond, graphite, and silicon dioxide, and this too I have covered in the website, so go there for further detail. But basically, for diamond, you just need to know that the carbon is joined to 4 other carbon molecules. And graphite, each carbon is bonded to 3 other carbon molecules, and they have a layer-like structure like so. Therefore, they sort of, they have a slippery nature because within layers, the layers are not, the attraction between each layer is not that powerful, so the layers can actually slide over pretty easily. But it's obviously fairly hard to break apart the atoms within each layer. Silicon oxide is fairly similar to the structure of a diamond, and you can see the diagram as follows. And the last thing we need to look at is metallic bonding. So metallic bonding is basically what you find in all metals, right? In metals, atoms will remove their outer electrons and become cations. Remember, metals will remove their electrons to become or obtain a full outer shell and therefore become cations. Cations are arranged in a lattice structure. Remember, lattice structure is basically another word for a regular sort of structure, like follows. And so the outer electrons are they're delocalized, meaning they can move sort of freely within the structure, and they form the sea of electrons. So what you have are a regular layer or regular arrangements of these cations and a free delocalized sea of electrons surrounding it. So what happens is the cations attracted by forces of electrostatic attraction to the sea of electrons surrounding it, and this attraction is what bonds the structure together, and this is metallic bonding. So this is just a quick example, and you know, these are named examples like zinc and sodium and what it would look like at a molecular level if you were to zoom up on it. Okay, so that's it for today, guys. Thank you for watching. As I said before, go to my website for extra revision notes. Like, share, and subscribe, and comment for extra exam tips, any sort of content requests, or even blog requests on the website. Thank you, and I'll see you in the next video. Hey guys, welcome to another igcse chemistry revision video. Today we're going to be covering, as you can see on the screen, the topic of stoichiometry. Now, I have just finished writing down all the notes on my website, freeexamacademy.com, and as you can see, it is quite comprehensive, so if you want to check that out, just visit the website, go under chemistry, under revision, and you'll find it there. But without further ado, let's begin. So this topic really was quite a challenge when I was studying IGCSEs, and initially I think it's because I didn't quite grasp the concept of it. Once you do grasp the concept, it becomes extremely easy, so that's what I'm going to try to do for you guys in this video. It does require a lot of practice from your end. You do need to achieve or attempt a lot of different questions to get the hang of it, but you know, you do need to have the foundations covered. So without further ado, we'll begin now. So first of all, you need to know how to construct the basic formula of a simple compound. So to do this, you need to know or understand the concept of valency, which is basically how many electrons does an atom need to lose or gain to obtain a full outer shell. So this is the periodic table that Cambridge will give you for your examinations. Right, so you can see here that you've got groups. You've got group 1, which is column 1, group 2, column 2. It skips the middle here, which is transition metals you don't really need to know, and then it goes to group 3, 4, 5, 6, and 7. We'll learn about the periodic table in a bit more detail later, but these columns or groups are really important because it tells you how many electrons these atoms within the group have in their outer shell. So beryllium, for example, is in group 2, therefore it has 2 electrons in its outer shell, whereas nitrogen has 5. Why that's important is because if you looked at my previous video, it means that you can determine what an atom needs to do in order to gain a full outer shell. For example, in terms of nitrogen, it needs to gain 3 electrons because it has 5. So it just needs 3 more to achieve a full outer shell, which is a lot easier than losing 5 electrons. So non-metals, which is on the right side of the sort of periodic table here, will tend to gain electrons to fulfill their atomic stability. Whereas on the left-hand side here, for example, lithium, it's got 1 electron in its outer shell, so it'd rather lose 1 electron to make itself have a full outer shell. And the valency is important because it also gives you the charge of whatever you're looking at, of the ion of the atom. For example, lithium here, if it turns from an atom to an ion, well, it's going to be losing 1 electron, so the charge is going to be -1. For oxygen, for example, it's in group 6, so it needs 2 extra electrons. When it gains those 2 electrons, then it's going to have a charge of -2. This will become a bit more easier for you as you progress through the course. But anyway, what you need to understand is mainly the concept of valency, right? So group 1, valency of 1 because it needs to lose 1 electron. Group 7, valency of 1 also because it needs to gain 1 electron. So whether it's losing or gaining, the valency is how many electrons need to be gained or lost in order to achieve a full outer shell, and that's very, very important. So the formula of a compound is simply obtained by swapping the valency numbers over, okay, and cancelling if possible. For example, you have potassium oxide, you've got the valency of 1 for potassium and 2 for oxygen. You swap the numbers and what you get is K2O. That is the formula for potassium oxide. Magnesium oxide, you have valency of 2 for magnesium, and also oxygen has a valency of 2. You swap the numbers over, but in this case you can cancel it out, and if you can cancel, you must cancel. What that leaves is MgO. So that's fairly simple. So the second step is to be able to write simple equations, right? This skill will actually naturally be developed as you sort of progress through the course, as you learn, certain rules of different chemicals reacting with different other substances and things like that. But here we'll focus on the idea of balancing equations because this is crucial. So the total number of each type of atom in the left hand side of the equation has to equal the right hand side. You can't just atoms can't disappear or be gained from one side to the other. It has to be absolutely equal. As you can see, magnesium plus oxygen giving you magnesium oxide. In this example, you can see that the equation is not balanced. You've got 2 oxygens on the left hand side but only 1 oxygen on the right. So what can you do to fix this? Well, you can't change the formula itself. You know that magnesium oxide has the formula of MgO. You can't simply just make it MgO2 to try to balance the equation just to add an extra oxygen here. You cannot do that. So, but what you can do is add numbers to the front of the compound or whatever it is. And so, for example, in this case, you can add a 2 in front of magnesium oxide, giving you 2 magnesiums on the right-hand side of the equation. So therefore, you have to add 2 onto the left-hand side. And when you do this, you have a balanced chemical equation whereby you have, an equal number of atoms of each particular element on both sides of the equation. And so these big numbers that you put in front actually represent the mole ratio. So every magnesium atom that is used in the equation, I suppose, or in the reaction, because it has a 2 in front and oxygen theoretically only has a 1 in front because it's got nothing there, it tells you that for every magnesium, because it's a 2-to-1 ratio, for every magnesium that is used, only half of oxygen is used. We'll learn more about the mole ratios later, and this becomes really important when you're doing calculations for stoichiometry. So there's a couple of definitions that you need to get your head around. We've got the relative atomic mass. That's represented as the AR, and this is the average mass of the naturally occurring atoms on a relative scale, whereby carbon has a mass of 12 units. So the definition itself is not really important, but what you do need to know here is that if you look at the periodic table, you've got the mass number. You should be familiar with mass number and proton number. We're talking about the mass number here. The mass number of the atom of that element is basically the relative atomic mass. That is key. So what you then have is relative formula mass, which is basically if you have a compound like magnesium oxide, the relative formula mass is just the addition or the sum of all the different relative atomic masses inside the compound. In this case, you've got magnesium, which has an AR of 24, and oxygen, which has an AR of 16. So the relative formula mass of magnesium oxide is just the sum of all those, which is basically 24 plus 16, giving you 40 grams. Okay, now this is all relative. It's relative mass, but it's important. And so magnesium oxide here has 40 grams, and why this is important is because 1 mole, okay, so 1 mole of any substance is basically defined as the amount of substance that contains 6 times 10 to the power of 23 atoms, ions, or molecules within that substance, okay? And that specific number is called the Avogadro's constant. What's really important here, of course, is the idea that 1 mole of any particular substance will have the weight of the relative formula mass of that compound. Okay, so for example, when we take a look at magnesium oxide here, 1 mole of MgO, okay, is defined as, the amount of substance that's contained 6 times 10 to the power of 23 magnesium oxide molecules. And altogether, that 1 mole will weigh 40 grams. And as you can see, 40 grams is the relative formula mass. Okay, 1 mole of magnesium will contain 6 times 10 to the power of 23 magnesium atoms. It will weigh 24 grams, okay, which is just the weight of a magnesium atom, okay, which is the relative atomic mass. Oxygen, okay, they're always in molecules. O2 will contain 6 times 10 to the power of 23 molecules again. It'll weigh 32 grams because the relative formula mass is 16 plus 16, which is 32. So please get your head around this because this is extremely important. So when we start to look at mole calculations, right? So all the calculations that we'll be doing will be about moles, and this is the concept that we talked about before. Okay, the 1 mole will be the mass, well, 1 mole has the mass of the relative formula mass or the relative atomic mass if there are just a single atom. Okay, so there are 3 main equations that you need to know, and it's these 3 here, and you need to be able to memorize this and be able to rearrange them off by heart. You need to be very familiar with these 3 equations. Also, you do need to know the concept of mole ratios. We briefly touched on this before, but a mole ratio is the ratio between the amounts in moles of any 2 compounds involved in a chemical reaction. So, if just take a look at 2 separate substances here. For example, magnesium and magnesium oxide. If 1 magnesium mole is used, then also 1 magnesium oxide mole will be formed in this particular equation, because the ratio between magnesium and magnesium oxide is 1 to 1 or 2 to 2, which cancels out to 1 to 1. And you'll sort of understand this a bit more when we go through certain examples, but for now, please make sure that you understand these 3 formulas. So we're going to go through the use of each of these formulas one by one. So in terms of mass calculations, okay, so the basics are that, let's take a look at some examples using the basics here. So 1 mole of water, which is H2O, how many grams is that going to be? You need to think to yourself, well, okay, so we talked about 1 mole having the relative formula mass. So the relative formula mass of H2O is just the added atomic masses, which is 18 because you add 2 to 16. 2 moles of magnesium oxide will simply be magnesium oxide's relative formula mass, which is 24 plus 16, which is 40, but you times that by 2 because 40 is the mass of 1 mole. You've got 2 moles here, so that's 80 grams, and you get the gist. So let's take a look at a bit more of a difficult example. So it says calculate the mass of magnesium oxide that is formed when 3 grams of magnesium reacts with excess oxygen. So I've wrote down a couple of steps here. First of all, you need to have a balanced equation. Then you calculate the moles of whatever substance that is in question. In this equation, we're talking about magnesium. Okay, so they say 3 grams of magnesium. So you need to figure out, well, how many moles is 3 grams of magnesium? And then step 3 is to review what the mole ratio is, right? Because they're asking for magnesium oxide. So then you take a look at the mole ratio between magnesium and magnesium oxide to calculate how many moles of magnesium oxide was formed from the reaction. Once you know how many moles of magnesium oxide was formed, then you simply use the equation that we talked about before, this equation here, to figure out what the final mass of the magnesium oxide was. So therefore, let's go through those steps one by one. You've got the balanced equation, and so if you want to calculate the moles of magnesium, all we need to do is chuck it into the formula, and the equation becomes 3 grams divided by the relative formula mass of magnesium, which is 24. So you get 0.125 moles of magnesium that was used in the reaction. So if 0.125 moles of magnesium was used, then you'd figure out the mole ratio, right? So you've got the number 2 in front of magnesium, and you've also got the number 2 in front of magnesium oxide, giving you a ratio of directly 1 to 1. What that means is, since 0.125 moles of magnesium was used, 0.125 moles of magnesium oxide has been formed. now that you know that 0.125 moles of magnesium oxide has been formed, you basically rechuck it back into this formula, you rearrange everything, and you get 0.125 times the relative formula mass, and that gives you 5 grams, which is the mass of magnesium oxide that was formed. So the main key point here, guys, is to initially calculate the moles and take a look at the mole ratio, take a look at the moles of whatever substance that was formed, and then convert that back into mass. And that's all done using this simple formula, as we took a look at before. So second of all is gas calculations. The basics of gas calculations is there's a really important idea here that 1 mole of any gas, right? Any gas will take up 24 decimeters cubed of volume at room temperature and pressure. Okay, so every single gas behaves this way, so that means 1 mole of oxygen will take up 24 decimeters cubed, 1 mole of chlorine gas will take up 24 decimeters cubed, every single gas will take up 24 decimeters cubed, 1 mole of that particular gas, that is. Okay, so if that was the case, then we can actually figure out the moles of any gas just by knowing how much volume it's occupying and vice versa. So therefore, we have derived this formula whereby the moles of any particular gas at room temperature and pressure, of course, is the volume of the gas divided by 24, because 24 is how much 1 mole would occupy. Remember, decimeters cubed is 1,000 centimeters cubed, and quite often they will tell you, they may say that the volume is, whatever in centimeters cubed, so you always have to divide it, or, you always have to convert it back to decimeters cubed before applying this equation. So let's take a look at an example. It's actually very similar to what we took a look at before. So the example says calculate the volume of oxygen at room temperature and pressure required to burn 1.4 grams of butane. Great. So 1.4 grams of butane. We take a look at the balance equation here and we think, well, 1.4 grams of butane, how many moles is that? We always want to think about the moles, not the mass, right? So 1.4 divided by the relative formula mass of butane, which is, I suppose, 12 times 4 from the carbons and 1 times 8 from the hydrogens, giving you 0.025 moles of butane that was used in the chemical reaction. The mole ratio here is 1 to 6. For every mole of butane, you get 6 moles of oxygen being used. What that means is, if 0.025 moles of butane were used, then 6 times that would have been used in terms of oxygen. So you simply times 0.025 by 6 and you get 0.15 moles of oxygen. Now that you have the moles of oxygen, you can actually calculate the volume using the equation before. So 0.15 times 24, okay, so this is a rearranged form of the equation, obviously, because now you want volume, so volume is moles times 24. So the moles is 0.15, you times that by 24, you get 3.6 decimeters cubed of oxygen. That is the volume of oxygen that is required to burn 1.4 grams, okay, of butane. The third one is solution calculations, whereby the formula is moles of the solid, or whatever it is the concentration times volume. Take a look at this example here. Calculate the volume of sodium hydroxide concentration of 0.16 needed to neutralize sulfuric acid, which has 20 centimeters cubed and 0.2 moles per decimeters cubed. So of course this is the concentration, this is the volume of sulfuric acid. So immediately you can see that you can calculate the moles of sulfuric acid. Okay, so what is the moles of sulfuric acid then? Okay, so you apply this equation here and you get concentration times volume. So 20 divided by 1,000, because this is in centimeters cubed, you want to convert that to decimeters cubed. 20 divided by 1,000, you times that by 0.2, which is the concentration, and you get 0.004 moles of hydrogen sulfate. Okay, which is a sulfuric acid. And so here, the mole ratio between sulfuric acid and sodium hydroxide, which is NaOH, is 1 to 2, meaning for every mole of hydrogen sulfate, you will need 2 moles of sodium hydroxide to neutralize it. So 0.004 moles of sulfuric acid, you times that by 2, meaning you need 0.008 moles of sodium hydroxide. But the question isn't asking you how many moles of sodium hydroxide you need, it's asking for the volume. So what you need to do is rearrange the equation, so therefore if you're looking for volume, it's moles divided by concentration. They give you the concentration, which is 0.16. All you need to do is 0.08 divided by 0.16, giving you 0.05 decimeters cubed or 50 centimeters cubed, which is the volume of NaOH or sodium hydroxide that is required to neutralize that specific amount of sulfuric acid. So thanks for watching, guys. That is it for today. It is a fairly confusing topic, but I hope that this has simplified it a little bit for you. As always, please like, share, and subscribe. Visit my website for more notes, and I'll see you in the... Hey guys, welcome to another igcse chemistry revision video. Today we're going to be covering the topic of electrolysis, and I have just finished writing down all the notes on my website www.freeexamacademy.com, so please go and pay a visit and check it out if you want. So without further ado, let's begin. I just want to go through the foundation and the basics of electrolysis with you today. So there's a couple of definitions. The main definition here that we'll be looking at is the electrolysis definition, which is basically the process of passing an electric current through a substance, bringing about a chemical reaction. In electrolysis, you have certain things that you use. For example, an electrolyte is the liquid substance that conducts electrical current when in molten or dissolved in water, with chemical reactions happening at the electrodes. The electrodes are pieces of metal or carbon through which the current enters and leaves the electrolyte. And you've got two types: the cathode, which is a negative electrode attracting cations, and here therefore it's named cathode, and an anode, which is the positive electrode, which attracts anions. So this is a very simple setup whereby you've got the battery pack or the power source connected to the two electrodes. One will be a negative one, which is the cathode. The other one will be a positive one, which is the anode. The cathode will attract cations from the electrolyte solution, whereas the anode will attract anions from the electrolyte solution. So reactions actually happen at these electrodes, and we need to know, what exactly is happening. So at the cathode, it'll usually be metal or hydrogen cations that get attracted, and the cations will basically gain electrons at the cathode to produce metals or hydrogen gas respectively. For example, if you had copper cations in the solution, the copper ions will jump over to the cathode, gain 2 electrons, and become a copper metal. Hydrogen, on the other hand, will again gain electrons, discharge itself, form the hydrogen gas, its molecular form. Aluminium, there's meant to be a plus in the middle here, but you get the point. It gains electrons again to form the aluminium metal at the cathode. The reaction happening at the anode is variable. It depends on whether the anode is inert, i.e. made of carbon or platinum, compared to whether it's not inert or reactive, whereby it's made of things like zinc or copper. Now if it is inert, okay, so it doesn't react, then what that will mean is that the anions will jump over to the anode, and as you'd expect, the anions will actually lose electrons to the anode and discharge itself. So for example, chloride ions will jump over, lose 2 electrons, form the chlorine gas molecules, whereas hydroxide ions will again gain some electrons, so lose electrons in this case, and discharge itself, forming oxygen and water at the anode. Now if the anode was reactive, made of zinc, copper, whatever, the metals in the anode itself will take part in the reaction instead. So for example, if you had an anode made of copper, at the anode you won't get anions coming over to discharge itself. What will happen is the copper atoms within the anode will actually lose electrons to form copper ions that move into the electrolyte. So when we think of an electrolyte, we need to think about what sort of ions are present inside it. And there are 2 main forms of electrolytes that Cambridge will give you. It's either molten or it's aqueous. Molten is basically the melted form of the substance, whereas the aqueous form is whereby the substance is dissolved in water, meaning it contains water as part of the electrolyte. So if it's molten, it's fairly simple. Molten sodium chloride, for example, you know that because it's just melted, the ions can only come from the substance only, so therefore you have the sodium and the chloride ions. Pretty simple. Aqueous, a little bit more difficult, because the water itself produces ions. So if you have any sort of aqueous solutions, you can guarantee that inside the electrolyte you'll actually find hydrogen and hydroxide ions, in addition to the ions coming from the substance, for example sodium chloride. So in this case, aqueous sodium chloride, you'll have the sodium and the chloride ions along with hydrogen and hydroxide ions, these ones coming from the water. So let's take a look at this example in a little bit more detail. So the aqueous sodium chloride containing these specific ions here, you can see that there's two cations, sodium and hydrogen ions, and you've got the chloride and the hydroxide anions. So at the cathode, obviously the cations are going to be attracted to the cathode because they've got opposite charge. So we need to think about the fact that only one of these can actually be discharged at the cathode. You can't, it's one or the other, you can't discharge both. Okay, so this is where the electrochemical series comes into play, because some ions have a lot more tendency to discharge than others. And so the lower down you are on the list, the more likely that will discharge as opposed to something else above it. So when we take a look at the cathode, we take a look at the ions hydrogen and sodium, and we can see that hydrogen ions are lower down on the list, meaning they have a greater tendency to discharge. So therefore, at the cathode, you'll actually get the hydrogen ions getting discharged rather than the sodium ions. Same thing with the anode, because the hydroxide ions are lower down on the list compared to the chlorine or the chloride ions. You actually get the hydroxide ions forming oxygen at the anode. What that means is you get sodium ions and chloride ions being remained in the electrolyte solution. So therefore, because the hydroxide ions and the hydrogen ions are getting used up, sodium chloride solution will become progressively concentrated throughout the process of electrolysis. Really important note here, despite the fact that hydroxide ions are lower down on the list in the electrochemical series, if the solution itself was concentrated, for example, Cambridge might say concentrated sodium chloride solution, then it will in fact be chloride ions that get discharged instead of the hydroxide ions, simply because you have a lot more chloride ions in the solution. So rather than the equation above, like so, you'll actually get chloride ions getting discharged to form chlorine molecules at the anode if it was a concentrated sodium chloride solution. And so what that will mean will be that there will be sodium ions and hydroxide ions being remained in the electrolyte, and so that is basically sodium hydroxide. If they don't say anything, then just assume it's dilute, okay? But if they do specify concentrated solutions, then you'll have to go with the fact that chlorine will actually be formed instead of the oxygen. So let's take a look at some examples here, right? So whenever you're looking at these examples, you have to think about three main things. One, what are the ions present in the electrolyte? Two, what are the reactions at the cathode or anode? 3, what is happening to the electrolyte? So if they say, for example, molten sodium chloride with inert electrodes, then you know that it's just sodium and chloride ions in the electrolyte, and so they will discharge accordingly, sodium being formed at the cathode and chlorine molecules or gas being formed at the anode. And that's fairly simple because it's just these two ions, then sodium chloride is being decomposed. Concentrated aqueous sodium chloride, we took a look at that before. The ions present are these four here. You get hydrogen being formed at the cathode, and at the anode you get chlorine being formed instead of oxygen because it's a concentrated solution. What that means is you have sodium and hydroxide ions remaining in the electrolyte, which makes sodium hydroxide. Concentrated hydrochloric acid, the ions present will be these three here. Reactions at the cathode, you'll form hydrogen, and at the anode you'll form chlorine again because this is a concentrated solution. In a dilute sulfuric acid, you get the sulfate ions, the hydroxide ions, and the hydrogen ions. Again, hydrogen will be formed at the cathode because that's the only cation here. At the anode, you'll find that you get oxygen because first of all, this is a dilute solution, and second of all, hydrogen, the hydroxide ions are lower down on the electrochemical series than the sulfate ions anyway, so these ones will be discharged rather than the sulfate ions. What that means is that the acid will become more concentrated as the hydroxide ions are being used up. So aqueous copper sulfate with inert electrodes. In this specific example, you have these 4 ions being present. At the cathode, you actually get copper being discharged rather than hydrogen ions. So you'll find copper being made. Again, that's because the copper ions have a greater tendency to discharge itself, and you can find that on the electrochemical series as before. At the anode, you'll find the hydroxide ions forming oxygen there. So the hydrogen ions and the sulfate ions will remain in the solution, which is basically sulfuric acid. Now, what if these weren't inert electrodes? What if they were actually copper electrodes? And we talked about this in briefly before, but then, so in this situation, the copper electrodes will actually react at the anode instead. So the ions presence are exactly the same. Okay, the only difference is that the anode is not inert. This means that rather than, as we looked at before, rather than the hydroxide ions being discharged here, what will happen is the anode itself will react. So the cathode reaction is exactly the same, but at the anode, the copper atoms will actually lose electrons to form copper ions, and the copper ions will go into the electrolyte solution. So that means that the copper will be deposited at the cathode, and it will become thicker compared to the anode, where copper is being used and removed, and therefore the anode will get progressively thinner. The electrolyte remains the same because the cathode is removing copper ions from the solution, but the anode is providing the electrolyte more copper ions, so it'll stay exactly the same overall. So this specific process is used to electroplate other metals with copper. So thanks for watching, guys. I hope this has helped. For more notes, go to my website www.freeexamacademy.com. It's got some extra notes on commercial and industrial uses of electrolysis, other bits and pieces that Cambridge wants you to know. Otherwise, please like, share, and subscribe, and I'll see you in the next video. Cheers. Hey guys, thanks for joining me in another video. Today we're going to be going through the topic of chemical energetics in igcse chemistry. So this is the relevant syllabus that you should take a look at before I start the video. So the main idea behind this topic is the difference between exothermic and endothermic reactions. Exothermic reactions are reactions that release heat. So that means the chemical energy of the reactants will actually be larger than the product. So overall, there's a decrease in energy because it's lost through heat. An endothermic reaction absorbs heat on the other hand, so you'll find that the chemical energy of reactants are smaller than the product. So overall, it has gained energy. And these two graphs sort of show that quite well. Here is an example of an exothermic reaction where the reactants have a energy level of about this much, but overall the energy level of the products are lower, so you can see that there's been a decrease in energy from the reactants all the way to the products. Whereas in an endothermic reaction, we see that the products have a higher potential energy than the reactants, so overall there's been an increase in energy, so therefore it's an endothermic reaction. So you do need to be able to replicate these graphs depending on whether you're talking about an exothermic or endothermic reaction, and quite often they'll give you the graphs and you are meant to interpret that. Now, one thing that I haven't noted so far is the activation energy. You can see that when you start off the reaction, the energy profile elevates quite rapidly, and the peak of that energy profile to the energy level of the reactants is called the activation energy. So for an exothermic process, is from this tip here all the way down to the energy level of the reactants, and for an endothermic reaction, it's from the tip of the hump here all the way down to the energy level of the original reactants as well. Bear in mind that the activation energy always has to be higher than the products, so you won't find the peak of the hump all the way down here. It has to be at least higher than the products. And the activation energy, by definition, is the minimum quantity of energy which the reacting species must possess in order to undergo a specified reaction. So I wouldn't overcomplicate things, but the activation energy is basically the amount of energy that is required to start off the reaction. And so they often give you sort of a blank energy profile diagram like this, and you are meant to label or draw arrows to show what or how much the activation energy is. So you should really study these two graphs and know it inside out. So the bond breaking and bond making process is also an important part of this topic. So bond breaking, when you're breaking apart a bond inside a molecule, is an endothermic process. So energy must be taken in order to break the bonds apart. On the other hand, the process of making a bond is an exothermic process. So when bonds are made, heat energy is basically released. So for example, they often give you a question like this. They give you a reaction and they say, is this reaction an exothermic or endothermic reaction? And they actually give you the bond energies that you should know, right? So all the relevant bond energies are down below here. So what we're going to do is, first of all, when you are thinking about a chemical reaction, what's ultimately happening is you're just rearranging the bonds from the left-hand side and rearranging that to form other molecules on the right-hand side, right? So by law of chemistry and physics, you can't have more molecules or more atoms on one side than the other because we are simply rearranging it. What that means is, if we were to break apart all the individual bonds on the left-hand side, we should be able to make whatever molecules or the products on the right-hand side. So using that information, let's break apart every single bond on the left-hand side and see what we get. So if you look at the relevant bond energies, we're breaking apart 4 CH bonds. So 413 times 4 is 1652. We're also breaking apart the bond between 2 fluorine atoms. So here it's 158. So 1652 added to 158 gives you 1810 kilojoules per mole. And again, we are breaking apart these bonds, and we talked about the fact that bond breaking is an endothermic process. So in order to break these bonds apart, the system gains 1810 kilojoules. On the right hand side, we're basically reforming the bonds that we've broken in different rearrangements, right? So let's think about what bonds we've made on the right hand side. We have 3 CH bonds in this molecule. So 3 times 413 gives you 1239. We have 1 CF bond in this molecule, and it's got 495 kilojoules of energy per mole. And we've also made 1 hydrogen to fluorine bond as well, which has an energy level of 565. So ultimately, if you add all those together, on the right hand side, we've basically got 2299 kilojoules of energy that's been lost because the process of making bonds, which is on the right hand side, is an exothermic process. So to sum that up, on the left hand side, by breaking apart all the bonds, 1810 kilojoules per mole of energy were gained, and on the right hand side, 2299 kilojoules per mole of energy was lost. So what we now have is that ultimately, if we were to look at it, we've lost more than we've gained. So it's a loss of 489 denoted by negative 489 kilojoules per mole of energy. Therefore, overall, because we've lost energy, it's an exothermic reaction. If we were to have gained more energy than we had lost, which would have been a positive number, then that would have been an endothermic reaction. So I hope that all makes sense. So hydrogen can be used as fuel, right? So the combustion of hydrogen is a highly exothermic process. It is quite commonly used as a rocket fuel or in experimental vehicles and fuel cells. So the advantages of using hydrogen as fuel is that they are very energy rich and you don't get any pollutants that are forming from it. For example, nitrogen oxides, these things are not formed by using hydrogen as fuel, and because nitrogen oxides are environmentally harmful, that can cause acid rain and things like that, it's overall a good thing that these are not produced. Disadvantages would be that they are expensive to produce and quite difficult and again expensive to store. So let's take a look at the details of how hydrogen fuel cells work. So much like electrolysis, you have an anode and a cathode. Anode being the positive and cathode being the negative electrode, and reactants are supplied to each electrode. So we've got the anode here on the left hand side and we've got the cathode on the right hand side. On the left hand side towards the anode, basically the fuel, which contains hydrogen, is supplied to the anode, whereas on the right hand side towards the cathode end, the air, which contains oxygen, is supplied there. So at the anode, what happens is the hydrogen molecules inside the fuel basically lose electrons and form ions in the electrolyte. And so you have this sort of chemical equation going on, hydrogen becoming two hydrogen ions along with electrons that have been lost. At the cathode, on the other hand, oxygen comes in and gains electrons, forming the hydroxide ions in the process. So these reactions are something that you should memorize. And so what then happens is in the electrolytes, you've got the hydrogen ions and the hydroxide ions that react to form water. And that in itself is an exothermic reaction and therefore releases heat, which drives, which supplies the energy, which is the whole point of the fuel cell. So one last point about this topic is regarding radioisotopes and how they can be used as a source of energy. So by definition, radioisotopes are isotopes, which of course are atoms that have the same proton number but different neutron number, that have an unstable atomic nucleus. And so they emit energy and particles as it changes from the unstable nucleus to the more stable form. And over 13% of the world's electricity is actually generated from uranium in nuclear reactors. And nuclear energy derived from this way actually has a fairly long-term nature and therefore sustainable. So uranium-238 are heavier and more stable compared to uranium-235, which is the radioisotope, which is rather unstable. So as uranium-235 basically stabilizes, it emits energy, and that energy can be used as a source of energy. So that's it for today's video, guys. I have been making exclusive past paper tutorials on Patreon, so if you're interested, please check it out and join me. I think it'll be really great help for you. Otherwise, visit freeexamacademy.com, where I write down all my sort of notes for igcse chemistry and things like that. So there are some pretty comprehensive notes there that you will find useful. Otherwise, please like, share and subscribe for extra content in the future, and I will see you in the next video. Cheers. Hey guys, welcome to another revision video on igcse chemistry. Today we're going to be covering the fundamentals of chemical reactions. So without further ado, we'll begin. So the first thing you have to understand is the differences between a chemical change and a physical change. A physical change relates to the changes in the physical states of matter, for example, ice turning into water, and a chemical change occurs more at a molecular level when two or more molecules interact with one another. Taking a look at chemical reactions in a bit more detail, we need to think about the collision theory, which states that two conditions have to be met for a chemical reaction to occur, one of which being two or more particles must collide, the other being that the particles, when they do collide, have to have sufficient energy in order for the reaction to occur. So, in other words, when two particles collide but they don't have enough energy, then no, the reaction won't occur, and oppositely, when they even if they have enough energy, when they don't collide, then of course that's just not going to work either. So these two conditions have to be met. And this is actually quite important when we take a look at the rate of a chemical reaction, because a lot of conditions like temperature, pressure, and all that sort of stuff actually affect things like collision rates of particles and the energy levels, and therefore affecting how quickly the reaction happens, or in other words, the rate of a chemical reaction. So this is exactly what we're going to be looking at now. There's a couple of things. The concentration is basically how many particles there are in a given volume, right? So a higher concentration suggests that there are more particles that are closer to each other, so therefore by chance alone the rate of collision will be higher, and that means the rate of a chemical reaction will thus be increased as well. Pressure works exactly the same way, except that it's only related to gases only. So a high pressure actually suggests that there are more particles in a given space, and therefore again the collision rate will be higher, and therefore increasing the rate of a chemical reaction. The temperature, ignore the word size, the temperature, if you think about it, a higher temperature will actually mean that the individual particles have more energy, but not only that, because they're traveling at a higher speed, the collision rate will also be higher as well. So both factors will be elevated, therefore increasing the rate of a chemical reaction as well. When we look at particle size, we're really only referring to solids, and it suggests that a smaller particle size actually has a lot larger surface area for collisions to happen, and therefore achieving a higher rate of chemical reaction. So I've sort of diagrammatically represented that here. If you can see that the red particles are trying to decompose this blue block of solid into its individual particles, I suppose. You've got two options. This big block, you can see that it's actually quite inconvenient for the red ones to act on, because it cannot access the middle atoms, because it's sort of surrounded by other blue particles. Whereas if you were to separate the blue particles into separate pieces, you've got a lot more area. Well, the red particles have a lot more area to work on now to decompose the solid, and therefore the rate of chemical reaction will be a lot higher. Now, when we take a look at something called catalysts, so these are substances that basically don't get used in the chemical reaction, but are there to increase the rate. And enzymes are found in our bodies, and that's an example of a biological catalyst. So let's take a look at the concept of reversible reaction. So this is when reactants form products. So this is meant to be reactants, and the products actually react to form back the reactants. For example, A plus B gives C, but C reacts back to, or decomposes back to give A and B. So in other words, we can sort of exemplify the reaction like so, with this double-headed arrow. So at some point in a reversible reaction, what will happen is the rate of the forward reaction will actually begin to equal exactly the rate of the reverse reaction. So this means that C is being formed at the same rate as A and B is being formed, because A and B make C, but C is forming A and B at exactly the same rate. What that means, therefore, is that the concentrations of all three of these things, i.e. the reactants and the products, will all remain constant, and when this happens, this is called an equilibrium. So the concentrations of these individual reactants and products in an equilibrium is called the position of equilibrium, and we'll talk about that in a bit more detail now. So let's put that up here again. So the position of equilibrium can actually shift, depending on how we alter the conditions of the environment. So when we talk about a shift, if we talk about it being a shift to the right, it suggests that more of A and B is getting used to make C. This means that the equilibrium concentrations of A and B will decrease, whereas the equilibrium concentration of C will actually increase. Oppositely, when we talk about a shift to the left, it's suggesting that more C is getting broken down to make A and B, so therefore the concentration of product C goes down, whereas the concentrations of A and B will inevitably elevate. So depending on the change in conditions, the equilibrium can either shift to the right or to the left, and we're going to be looking at that in a bit more detail in this slide. So for the sake of the argument, we're going to say that A plus B gives C again. I've added some extra information. We'll say that the forward reaction is exothermic, whereas the reverse reaction is endothermic, and this is important. You'll see why later. But what's really important to understand here is that the position of equilibrium will always shift in the direction to oppose the change being imposed. So you'll understand what this means as we go through each of these examples. For example, concentration, when we increase the product concentration, right? For example, if we increase the concentration of product C, that will shift the equilibrium to the left, because so remember, if we increase the concentration of C, the equilibrium will try and oppose that change to reduce the concentration, and the way that it can do that is shift the equilibrium to the left by producing more A and B from C, therefore decreasing concentration of C. Exactly the same thing if we were to forcefully decrease the concentration of C, and manipulate the environment that way, then the equilibrium will actually shift to the right, as if to make more C. So I hope that makes sense. And similar thing, if we were to increase the reactant concentration, for example the concentration of A, you would assume that the equilibrium will actually shift to the right in order to remove or reduce the concentration of A, because we just increased it and wants to oppose that change and decrease it. So that's sort of how this whole thing works. When we talk about the temperature, exactly the same thing. That's why I gave you this extra information above. If we were to increase the temperature, what the reaction will do, will try to decrease the temperature, so therefore it will favor the endothermic reaction, which means that the reaction is taking in heat. So it will shift, in this example, it will shift the equilibrium to the left. If we were to decrease the temperature, it will actually favor the exothermic reaction, because it's going to try to increase the temperature, and it's obviously opposing what we're doing, so it'll shift the equilibrium to the right if we were to do that. Now, when we talk about pressure, I want you to take a look at this diagram to the right here, because it's actually quite important. Pressure can be basically defined by the individual gas molecules hitting against the walls of the container in which it's in. So if you have more particles in this given space, then there'll be more collisions with the wall, and therefore the pressure will be higher. If you've got a smaller amount of particles, then there'll be less particles hitting the walls, and therefore less pressure. So pressure really only is to do with gases, right? So high pressure suggests that there is a lot more particles in that given space compared to lower pressures. So if we were to increase the pressure again, the equilibrium will shift to the side, or it will shift towards trying to decrease the pressure, and the way it can do that is to favor the side that has lower number of particles. If you look at it here, the left hand side in this example has 2 particles, but the right hand side only has 1. So therefore it will actually shift the equilibrium to the right in this instance, towards the side with a lower amount of particles, because that gives lower pressures. If you were to decrease the pressure, it will be the opposite. It'll try to increase the pressure, and the way that it can do that is shift the equilibrium position towards the side that has more particles, because more particles means more particles hitting against the walls of the container, I suppose theoretically, and that gives rise to higher pressures. So in this case, decreasing the pressure will shift the equilibrium position to the left. And a catalyst actually doesn't affect the equilibrium at all, so don't get tricked by this in an exam. It's only there just to increase the rate of reaction, and it increases the speed of both the forward and the reverse reaction. It doesn't affect the position. So lastly, we're going to be looking at the concept of redox. It's shortened for reduction and oxidation, and this can be demonstrated in 2 different ways, and both are absolutely correct. One is the oxygen gain or loss, right? Oxidation is the gain of oxygen, whereas reduction is the loss of oxygen. So in this example to the right here, copper oxide can be you can say that it's been reduced because it goes from copper oxide to copper, therefore it's lost in oxygen. But if you think about it, hydrogen on the other hand has gained oxygen, so therefore it's you can say that the hydrogen has been oxidized. Another way of looking at redox is the electron gain or loss. So oxidation is defined as the loss of electrons, and reduction is the gain of electrons. So if you look at this example here, magnesium added to chlorine giving magnesium chloride, you can see that there's absolutely no oxygen involved, but there certainly is some sort of electron transfer. So what we're going to be looking at is how magnesium, right, the atom has evolved or changed itself into the ionic form in this ionic structure of magnesium chloride. So if you take a look at it separately, magnesium has actually lost 2 electrons and to form the magnesium cation, and therefore because it's lost electrons, it's said to have been oxidized. Whereas chlorine, on the other hand, the molecule has gained electrons to become the ion, therefore it's an example of reduction because it's again gained electrons. So I hope you guys found that helpful. Please visit my website www.freeexamacademy.com for more detailed notes and guide on the topic. Otherwise, please like, share, and subscribe. And I know that it's fairly close to exams, and also if you have any further questions, just comment and I will try to answer. Thanks, and I'll see you in the next video. Hey guys, welcome to another video on this channel. Today we're going through igcse chemistry, acids and bases, really just touching upon the key concepts that you're required to know in this topic. So without further ado, we'll begin. So we'll start off with the pH scale, a scale that exists from 0 to 14, 7 being exactly neutral, and going down the scale, the more acidic the solution becomes, and going up the scale, the more basic the solution becomes. So therefore, the lower the pH, the more acidic the solution is, with a higher concentration of hydrogen ions in aqueous. The higher the pH, the more basic the solution becomes, with a higher concentration of hydroxide ions in aqueous, and this will make a bit more sense when we take a look at the definitions of an acid and a base. But before that, taking a look at the pH scale, the pH of a chemical can actually be figured out using the universal indicator paper. This universal indicator paper, basically when you add it to a chemical, it tells you the pH of that specific chemical using this color coding system, right? And each color basically correlates to a specific pH, as you can see in this chart. So the simple definition of an acid is a substance that generates hydrogen ions, or protons, because that's what they are essentially, in aqueous. The definition of a base is a substance that generates hydroxide ions in aqueous. Bases are generally metal oxides or hydroxides, and a soluble base is what we call an alkali. So other than the universal pH indicator that actually tells you what the pH of a chemical is, there are 2 other indicators that you need to know. These ones don't actually tell you what the pH is, they simply just tell you whether something is acidic or basic. First of all, litmus paper. If you were to use a red litmus paper, because it comes in 2 variations, red or blue, if you use the red litmus paper and you put it in an acid, there will be no changes, it will remain red. If you add it to an alkali, it'll actually change color from red to blue. Oppositely, if you use a blue litmus paper, you put it in an acid, it will change color from blue to red, and it will make no changes. If you put it in an alkali, it will remain blue. So therefore, you could say that an acid will change a litmus paper, turn litmus paper red, and an alkali will turn litmus paper blue. The other one we need to know is methyl orange. In an acidic solution, the methyl orange indicator will remain orange. If you put it in an alkaline solution, it will turn yellow. So, when an acid and a base react, you get something called a neutralization reaction. You get the salt, which is a ionic compound that results from the reaction along with water. But what's really happening is the hydrogen ions from the acid react with the hydroxide ions from the base to create water, which is a neutral chemical, and therefore we call this neutralization. So, when we take a look at the properties of acids, there are three main reactions that Cambridge wants you to be able to recall. So, acids plus metals will also always give you salt and hydrogen. So, in this example, magnesium will react with hydrochloric acid, and the salt will be the metal ion combining with the chloride ions and hydrogen chloride, and therefore you get magnesium chloride along with hydrogen. We looked at the neutralization process before. Acids and bases will give you salt and water. So here in this example, copper oxide reacting with sulfuric acid, you get copper sulfate with water being formed as a part of the reaction. Acids plus carbonates are similar. You get salt, water, but you also get carbon dioxide. So in the example, hydrochloric acid and sodium carbonate, the salt will always be a combination of the metal ion, which is the sodium ion, with the anion from the acid, which is the chloride ions. When they combine together, you get sodium chloride, salt here, and along with the two byproducts of water and carbon dioxide. So it's fairly simple to remember. When we take a look at the base again, we take a look at neutralization. We looked at that before, but the only other thing you need to know is bases plus ammonium salts, giving you salt, ammonia, and water. So if you get ammonium chloride, which is ammonium salt, you add that to sodium hydroxide, what you'll find is you'll produce sodium chloride as a result, along with ammonia and water. So what defines a strong acid or a base? Well, acids, remember, release hydrogen ions in aqueous, and bases release hydroxide ions. And the concentrations of these respective ions actually dictate the strength of the acid or a base, right? So a strong acid will actually have a very high concentration of hydrogen ions, resulting in a low pH. And a very strong base will have a very high concentration of hydroxide ions, resulting in a high pH. So a strong acid or a base will therefore release a lot of these hydrogen or hydroxide ions, respectively. And this is simply because the molecules are completely ionized in aqueous solution, and this is denoted by a single arrow. I'll tell you what I mean now. So taking a look at this example here, hydrochloric acid is of course an acid, and it's a fairly strong acid with a pH of around 2. So what happens is all these hydrogen chloride molecules will actually break down into its ionic product. So for this case here, you'll get hydrogen chloride or hydrochloric acid breaking down into hydrogen ions or protons and chloride ions completely and fully. So basically, if you have 100 molecules of HCl, you can expect all of them to break down to form these ions. Same thing here, if you have 100 sodium hydroxide molecules, you can expect all of them to basically break down into sodium ions and hydroxide ions, and therefore you result in a lot of hydroxide ions here, therefore raising the concentration. And in this scenario here, you get a lot of hydrogen ions as a result of the complete dissociation. If oppositely, a weak acid or base will release a small amount of hydrogen ions or hydroxide ions respectively. This is because molecules are only partially ionized in aqueous solution, and we look at that with a double arrow. So ethanoic acid, if you have 100, maybe only 2 or 3 of those molecules will actually break down to form the ions, and therefore you don't actually have a lot of you don't have a high concentration of hydrogen ions in solution. Same with the base, the weak base here, ammonia. You don't really get a lot of hydroxide ions formed because only a small amount of these molecules actually dissociate to make the ions. So therefore, the low concentrations of hydrogen ions and hydroxide ions will result in a weak base or a weak acid. So let's take a brief moment and look at some oxides. So most metal oxides will be basic, and soluble bases, again, we call those alkalis, right? Remember, bases turn litmus paper blue, but only if they're alkali, right? So insoluble bases that do not dissolve in water will not affect litmus paper at all. It will not change it. Non-metal oxides are usually, it can be neutral or acidic. So neutral oxides are oxides such as water, nitrogen oxide, carbon monoxide, and because they're neutral, they do not react with acids or bases. Acidic oxides like sulfur dioxide, sulfur trioxide, carbon dioxide, and oxides of phosphorus will turn litmus paper red, as we talked about before, and because they're acids, they will neutralize bases in the neutralization process. Amphoteric oxides are oxides that can react with both acid or a base to form salt and water. This means that these oxides have properties of both an acid and a base, and examples of such are zinc oxide and hydroxide, along with aluminium oxide and hydroxide. And there are a couple of reactions here that you need to know. So you need to know zinc oxide and hydroxide and aluminium oxide and hydroxide acting as both an acid and a base, and these reactions here summarize that. So above here is these compounds are reacting as an acid because they're reacting with a base, and so ultimately you get the salt and water. You just need to figure out what the formula of the salt is. Same thing here, behaving as a base, they're reacting with the acids, and therefore again you get salt and water. You just need to figure out what the formula of the salt is, and that's fairly easy. You just combine the metal from the oxide, and you combine it with the anion again from the acid, which is the nitrate ion here in this case, along with the zinc. So, we defined an acid previously as something that releases hydrogen ions in solution, and a base as a chemical that releases hydroxide ions in aqueous. So, we're going to revise that definition a little bit. There's a couple of definitions. The first definition that we looked at before is the main one, but here is the second definition, and Cambridge also wants you to understand this. Acids are proton donors and bases are proton acceptors, right? And this sort of does come into, this aligns with what we talked about before. Acids release hydrogen ions and, bases release hydroxide ions. And remember, this is the neutralization process. But if you look at this reaction between an acid and a base, you'll realize that the hydrogen ions come from the acid, and it gets accepted by the hydroxide ions, which comes from the base, and therefore forming water. So in reality, what's been happening is the acid donates a proton, which is this hydrogen ion here, and the base actually accepts that proton to make water. So this is a definition that you need to know. Acids being a proton donor. Here, this diagram here sort of takes it a little bit further, but ultimately the acid, which has the hydrogen ions, donates it to the base, and you get the products here. You don't really need to dig too deep into this, just need to know the definitions. So that's it for today, guys. For some extra content, go to www.freeexamacademy.com. We take a look at salt preparation and ion identification there. Without further ado, we'll just end this video. Please like, subscribe, and share the video as well, and we'll see you in the next video. Hey guys, welcome to another igcse chemistry revision video. Today we're covering the topic of metals, and these are a couple of key points that the syllabus wants you to be able to understand. We're not going through metal extraction. If you want to know more about that, go to my website www.freeexamacademy.com. I've covered that in detail there, but otherwise in this video we'll be covering all of these things here. So the physical properties of metals are usually that it's quite shiny. They're really good conductors of heat and electricity. They're usually fairly they're high in density. They're malleable and ductile due to the nice lattice arrangement of the cations and the metallic structure. Usually solid in room temperature, and they're sonorous, suggesting that they make bell-like sounds when struck. In terms of the chemical properties, they have the chemical, the classic metal plus acid reactions, and we've covered this in the acids and bases topic, but ultimately you get the salt and hydrogen when you add them together. Metals will react with oxygen to produce the metal oxide, and metals will also react with water. Now, depending on the reactivity of the metals, they can either react with cold water, like sodium and potassium. They're fairly reactive metals, and you get the metal hydroxide salt along with the hydrogen. But other metals such as zinc are less reactive. They don't react in cold water, but they do react in steam. And so if you were to add a metal plus steam, you'd get the metal oxide with hydrogen. Alloys are basically a mixture of two or more metals, or a mixture of one or more metals with a non-metal. Sorry, this is meant to be non-metal. And so alloys are harder than pure metals, and the reason for that is because in an alloy, you have different sized atoms, and that will make the layers of the metallic structure less mobile, and therefore preventing them from slipping. So this is basically a diagrammatic representation of what an alloy might look like. You can see that there are various different atoms going on here, and the structure is obviously a bit less regular than a normal metallic lattice, and therefore the alloy is harder in structure than a pure metal. So there are a couple of examples. Brass is a mixture of zinc and copper. A mild steel is a mixture of iron with a small amount of carbon, and stainless steel is a mixture of iron, nickel, and chromium. So one of the key topics of this part of the syllabus is the reactivity series, which is basically a list that lists that orders metals from the most reactive to least reactive, and you've got carbon and hydrogen in here as well. They're obviously not metals, but they're included in this list. So we need to think about what is reactivity. So especially when we talk about metals, reactivity is dictated by a metal's tendency to become ions or cations, right? So the more reactive a metal is, the greater the tendency the metal has to form metallic ions, right? So basically what this means is, for example, potassium, which is the highest on the list, has a higher tendency to form potassium ions than, say, calcium, and so forth. Right, so this becomes a bit more apparently important later on when we talk about displacement reactions and things like that, but for now we'll move on. And so now that we know that there's obviously variations in reactivities amongst metals, you can actually sort of you can look at the reactions of all of these metals with certain things like water, dilute hydrochloric acid, and potential reduction of the metallic oxide with carbon to deem which metals are more reactive than the other. So there's obviously a strict pattern here. So potassium and sodium, they're quite reactive, and they react violently with cold water, whereas as you go down the list, the reaction becomes more dilute. So calcium reacts fairly quickly with cold water, but not vigorously. Magnesium has a fairly slow reaction in cold water. And zinc and iron, they don't react with cold water at all, but they do react with steam. And the copper metal doesn't actually react with steam or water, cold water, suggesting that it is the least reactive amongst all of the metals that we took a look at before. We can also sort of figure out the same pattern when we take a look at the reactions of these metals with dilute hydrochloric acid, whereby the potassium and sodium, they are fairly explosive and, dangerous even, and the reactions become less and less vigorous as we go down the list. Of course, this is the full list of metals in the reactivity series, but for your sake, you really only need to know these metals that that's been listed on this table here. The third column is the reduction of the metal oxide with carbon. So this is suggesting that potassium, sodium, and calcium oxides cannot be reduced with carbon. Whereas zinc, iron, and copper oxides can be reduced by heating with carbon, and we'll take a look at this in a bit more detail because it can be fairly confusing. But ultimately, the fact that these metal oxides down below can be reduced by carbon is suggestive of the fact that they are less reactive than the metals above. Okay, so if we take a look at that in a bit more detail, right? So this is the reaction between zinc oxide and carbon. So when you heat them together, zinc oxide becomes zinc the element, and carbon basically steals the oxygen from zinc oxide to form carbon dioxide. So ultimately what's happened is zinc oxide loses an oxygen to carbon, therefore it's been reduced, because reduction is the loss of oxygen. That's one of the definitions, right? So this is only possible because zinc is lower in the reactivity series than carbon. So basically carbon is more reactive than zinc. And remember, so zinc being a fairly low metal of low reactivity suggests that zinc would much prefer to be in the elemental form rather than the ionic form, because it has a fairly low tendency to form ions. So basically that shows that because carbon is higher on the reactivity series than zinc, it has the capability to reduce zinc oxide. Okay, so if we were to sort of narrow it down and put it into simple terms, carbon can only reduce the oxides of metals that are less reactive than itself or below it on the reactivity series. So if we take a look at the reactivity series here, everything below carbon here, all of these metal oxides can be reduced by carbon, whereas all the oxides above carbon cannot be reduced. Okay, so that's just why that is why in this table, if you look at the zinc oxide, iron oxide, and the copper oxide, these can be reduced by carbon, therefore suggesting that it is these metals are less reactive than the metals above it. So, talking about the reactivity series, another really important concept to learn is displacement reactions, which basically involved one ion replacing another in the reaction. So, whether or not a metal can displace another metal that exists in a compound is strictly dependent on their relative reactivities. For example, if you add zinc to copper sulfate, what you'll find is that you actually get an end result of zinc sulfate with copper. So let's look carefully at what's actually happened. Zinc has become a zinc ion because it was an elemental form on the left hand side, but now it's in an ionic form combined with sulfate, so therefore it is a zinc ion. Whereas copper sulfate, the copper ions and copper sulfate has actually transformed into the elemental form, like so. Okay, so basically zinc has replaced copper and copper sulfate, and this was possible because zinc is more reactive than copper, and again, reactivity wise, zinc has a higher tendency to become an ion. Okay, so zinc would much rather prefer to be an ion in this scenario, and copper, which will much prefer to become an elemental metal rather than an ion. So therefore they swap places because it's a win-win situation. Whereas if you had zinc added to magnesium chloride, magnesium is perfectly happy where it is at the moment because it's more reactive than zinc, and it has a higher tendency to remain in ionic form, so it will remain there, so therefore you won't get any reaction at all. So basically, if we were to sum it up, a metal can displace another metal in a compound only if it is more reactive or higher up in the reactivity series. Zinc is higher up than copper in the reactivity series, therefore they swap places here. Zinc is not higher than magnesium, and so you don't get any sort of displacement reaction happening in this scenario. So, let's take a look at something called decomposition. This isn't exactly to do with the reactivity series, but one thing to note is basically the higher up a metal is in the reactivity series, for example potassium, when they form a compound, the compound is a lot more stable than say a metal compound of a lower reactivity. So say magnesium chloride, a magnesium chloride molecule is more stable than say zinc chloride. Okay, but ultimately decomposition reactions occurs when one reactant breaks down into two or more products, and there are three main compounds that you need to sort of memorize in terms of decomposition. So first of all is the metal hydroxide. A metal hydroxide, when you heat it up, it'll decompose into the metal oxide and water, just like this example here. A metal nitrate will decompose into into the nitrite and the oxygen if it's a sodium or potassium nitrate. Okay, so the more reactive nitrate, in this example sodium or potassium nitrates, will form the nitrite, which is the NO2 salt with oxygen. Every other nitrates that are not sodium or potassium nitrates will actually form the metal oxide, nitrogen dioxide, and oxygen, like this example here. So this is just something that you'll have to memorize. Metal carbonates, fairly easy. They heat up, they decompose into the metal oxide and carbon dioxide. So as long as you know what's formed, you just sort of write it out and then you balance the equation later. So that's it for today, guys. Just go to my website www.freeexamacademy.com for more info. Please like, share, and subscribe. And I just wanted to tell you guys that Patreon will be launching very, very soon, and there will be some really, really valuable exclusive content on there. And I will be making a video on that separately in the near future, just to give you guys a heads up. But otherwise, I'll see you in the next video. Thanks, guys. Hey guys, welcome to another video. Today we're going to be going through the topic of air and water, and so these are the relevant topics that we'll be going through. So have a quick read and we'll begin the video. So air is composed of nitrogen being 78% and oxygen being 21%. The other percentage is comprised of argon and other noble gases along with carbon dioxide. So nitrogen and oxygen can be separated from the air by liquefying the air and then separating the two gases by fractional distillation. So air is basically first filtered to remove dust and things like that, and then cooled to around negative 200 degrees, which is when air, the gas form, turns into liquid air. So once you have liquid air, you can use fractional distillation to remove or separate the two elements. So liquid air is passed into the bottom of the fractionated column, and of course fractional distillation utilizes the idea that the bottom part of the fractionated column has a different heat or is warmer than the top part. And we can see that because the entering temperature is around 200 degrees negative, and you've got negative 185 at the bottom and negative 190 at the top, so the bottom is warmer. So what happens is, because nitrogen liquefies at negative 196 degrees, the bottom part here, which is negative 185, is way too hot. What that means is that the liquid nitrogen that comes in with liquid air will actually boil down at the bottom, and it will rise to the top where gaseous nitrogen is taken out and stored. The bottom part, oxygen, the liquid oxygen, can be sort of piped out down at the bottom, and that's pretty simple, and we can store that. So we've essentially separated nitrogen and oxygen, as simple as that. The pollutants of air mainly are carbon monoxide, sulfur dioxide, oxides of nitrogen, and lead compounds, and you need to know the sources of these pollutants along with how it can affect our body and the environment, basically. So carbon monoxide is caused or produced from the incomplete combustion of carbon-based fuels. So normally, if you burn carbon in sufficient oxygen, you'll actually form carbon dioxide. In incomplete combustion, for example, when you don't have enough oxygen, you'll actually form carbon monoxide instead of carbon dioxide. So carbon monoxide is detrimental to our health because it binds permanently to red blood cells, and the red blood cells normally carry oxygen. So basically the carbon monoxide prevents the transport of oxygen, and that can lead to serious problems. So here is the chemical reaction that is relevant to that. Sulfur dioxide is formed by burning fossil fuels which contain sulfur, and the sulfur can actually cause acid rain, and that can cause deforestation and building damage and things like that. And so of course sulfur added to oxygen will give you sulfur dioxide in this equation here. The oxides of nitrogen is made when nitrogen and oxygen react at really high temperatures, and you find that inside car engines. Bear in mind that it's not actually the combustion inside the engines that are causing these pollutants to form. The oxides of nitrogen, again, is just caused because there's high temperatures inside car engines, and that causes the nitrogen and the oxygen inside the air to react with each other. And oxides of nitrogen can cause severe respiratory problems, along with the fact that it can also cause acid rain as well. So here are two equations that you should know for that. Lead compounds are present in lead petrol, and so ingestion of these things can actually damage the brain and have pretty bad consequences in terms of what it does to our nervous system in general. So one way to counteract the production of oxides of nitrogen inside car engines is to install a catalytic converter. So this is a pretty smart way of sort of neutralizing these pollutants. So basically what it does is it catalyzes the reaction between nitrogen oxide and carbon monoxide, producing carbon dioxide and nitrogen. And as you know, carbon dioxide isn't that bad. It can also catalyze the reaction between nitrogen dioxide along with carbon monoxide, and it forms again carbon dioxide and nitrogen. And this is really smart because it removes two pollutants, which is nitrogen oxide and carbon monoxide, at the same time to produce two fairly non-harmful elements, or sorry, not elements, just products. So let's talk about rust, right? So rust is hydrated iron oxide. That's all that it is. So hydrated means that there's water, and iron oxide is just simply the product of, or the ionic product of iron combining with oxygen. So therefore, rusting can only happen in iron or steel, because steel contains iron, and therefore only iron or steel can be termed rusting. Everything else is technically corroding, right? So not only do you need iron or steel for rusting to happen, you need water and oxygen, because obviously it's the reaction between iron and oxygen, and inclusive of water. So all three things have to be present. So a couple of methods of rust prevention would mainly be to sort of offer some sort of physical boundary so that the iron doesn't react with oxygen. So it can be, for example, painting, using oil or grease, which acts as a coating but also effective as a lubricant in moving parts of machinery and things like that. Perhaps coating with plastic, planting, and galvanizing. So galvanizing is important because it offers sort of something called sacrificial protection. And we'll look at that in a bit more detail. Yeah, so the first thing about sacrificial protection is the idea that there's a difference in reactivity between zinc and iron. Remember, in this reactivity series, zinc is higher up than iron, suggesting that zinc is more reactive, which means that zinc would much prefer to be in its ionic form rather than iron. So it has higher tendency of zinc to go into its ionic form rather than iron. So what happens is that here, this is the standard coating to the right? So this is not sacrificial protection, and this is just the standard idea that you can coat the iron with tin. But the problem is, when the tin wears off and there's exposure of the iron, the oxygen can easily come and oxidize the iron, and so the iron goes from iron element into the ionic form, which is iron cations, basically, Fe2+. And as that happens, you start to lose the iron and basically cause rust. Now, in sacrificial coating, you coat it with zinc rather than tin, and of course, zinc is more reactive than iron. So even if you do get a little bit of hole forming and the breakdown of the zinc coating, what will happen is that the oxygen doesn't oxidize the iron, but it actually reacts with the zinc instead. Remember, because zinc is more reactive than iron. So rather than the iron corroding or rusting, the zinc will take its place. Therefore, it sort of sacrifices itself for the iron, and therefore you don't get as much rusting going on. So here are some chemical tests for water, right? So water will basically turn anhydrous copper sulfate from white to blue. So here is the reaction. You got copper sulfate, which obviously does not contain any water, which is the anhydrous form. You add that to water and you get the hydrous or hydrated copper sulfate. So anhydrous copper sulfate has a white color, but the hydrated copper sulfate will have the blue color. So if you were to add something to anhydrous copper sulfate and it changes color from white to blue, then you know that water must be present. Similarly, water will turn anhydrous cobalt chloride from blue to pink. And you can use like a cobalt chloride paper for this, but ultimately the cobalt chloride anhydrous form will be blue, and if you sort of add any sort of water to it, it will turn pink, as you see there. So a couple of sort of points about water. The treatment of water includes filtration through sand and gravel to remove undissolved solids from it. You can treat that with chlorine to kill off bacteria, and then you can supply that to consumers, therefore, because it's safe to drink. There's a couple of uses of water, and many of these are sort of self-explanatory and common sense, but you can use it for drinking, growing food, producing goods, recreation even, maintaining ecosystems. There's a whole lot that you can list here. Some implications of poor water supply would be the health issues from lack of sanitized water, which can obviously cause a lot of different problems, and reduced crop yields, because obviously water is important to grow plants. So thank you for watching, guys. That's it for today's videos. Please like, share, and subscribe. And if you haven't heard already, I have started a Patreon channel, so please think about joining and supporting me there. You will gain access to a lot of past paper tutorials. I've completed 15 years worth of tutorials for biology, and I will be moving on to chemistry very, very soon. So look out for that, but otherwise I will see you in the next video. Cheers! Hey guys, welcome to another igcse chemistry revision video. Today we're going to be going through two topics. We're going to be going through sulfur and also carbonate. So without further ado, have a quick look at the syllabus content. It's not a long topic for either of these, and we'll begin the video. So the sources of sulfur is found mainly in underground sulfur beds in the USA, Mexico, and Poland. Natural gas and petroleum contain a moderate amount of sulfur compounds. These have to be removed and are also an important source of sulfur. Metal sulfides occur as ores, and one example of this is zinc blende, and you should know of this already in terms of the extraction of metals. And if you don't know that, you should go and revise that as well, because they tend to ask you a lot about that in exams. So when we take a look at sulfur dioxide, which is basically an oxide of sulfur, sulfur dioxide is mainly used in the contact process. And the contact process is a fancy word for the process that manufactures sulfuric acid. And you'll find sulfuric acid in a lot of different places, and there's a lot of different uses that we will be going through later on. But for the sake of your sort of experience and things like that, you would have found sulfuric acid widely spread in your laboratory rooms and things like that, and it is an example of a strong acid. Sulfur dioxide is also used in bleach, in the manufacture of paper from wood pulp, and as a preservative as well for killing bacteria in food. So we talked about sulfur dioxide being used in the contact process, which is the process that makes sulfur dioxide. So let's just go through the steps, because this is quite important, and if they're going to be asking you any sort of question about sulfur, generally it would be about the contact process. Sulfur is basically burnt in air to form sulfur dioxide. Simple. Sulfur plus oxygen gives you sulfur dioxide. This is then mixed with oxygen to form sulfur trioxide, and this is important here that this is in equilibrium. So we've got the double arrow suggesting that it's got the forward reaction and also the backward reaction as well. But either way, sulfur dioxide reacts with oxygen and you form sulfur trioxide as the product. So the reaction between sulfur trioxide and water inherently produces sulfuric acid. Unfortunately, this isn't exactly what we do in the contact process, despite the fact that it works, because this reaction between sulfur trioxide and water is very, very violent and explosive. And so you can't really do that to make sulfuric acid. Instead, what you do is basically add sulfur trioxide. You dissolve that or add it into sulfuric acid or concentrated sulfuric acid, and we produce something called oleum. So here's the reaction here. You got sulfur trioxide. Instead of just putting it straight into water, you put it into concentrated sulfuric acid, H2SO4, and what you get is this compound here, H2S2O7, which is oleum, and you do need to know that. And what you then do is add oleum to water, and that will give you 2 moles of sulfuric acid, as the last equation shows you here. So that's a roundabout way of doing things to make sulfuric acid. because the reaction between sulfur trioxide and water is way too explosive to carry out in this procedure. There's a couple of things that you need to know regarding this whole process and in terms of the conditions that is required, because they like to ask you that as well. So the conditions are 400 to 450 degrees Celsius. The pressures are between 1 to 2 atmospheres, and the catalyst that is used is vanadium 5 oxide. So the properties and uses of sulfuric acid. When we think about dilute sulfuric acid, despite the fact that it's dilute, it's still a very strong acid, and it'll show characteristics of typical strong acids. And of course, strong acids are acids that completely ionize in aqueous solution, and they have characteristic acid-like reactions, say with metals, with bases, and whatnot. The general uses of dilute sulfuric acid would be to make fertilizers, treat metals, and remove oxidation before painting, laboratory reagent that you find in your labs at school, acid and car batteries, dye, fiber, and paint manufacture, all that sort of stuff are fairly common uses. When we talk about concentrated sulfuric acid, the properties, of course, would again be that it's a strong acid, it's a very powerful dehydrating agent, and it's a very powerful oxidizing agent as well. The uses would be similarly to make detergents. It can be used as a catalyst, and it can also be used as a dehydrating agent. As we talked about above, one of the properties are that it is a dehydrating agent. So moving on to carbonates, a lot of this is focused on calcium oxide. And so the manufacture of calcium oxide is something that we'll have to talk about. So let's actually get some terminologies sort of set first. So calcium carbonate, another word for that is limestone. So don't get confused if they use limestone in an exam, because it simply means calcium carbonate. Now, calcium carbonate or limestone decomposes into calcium oxide, which is lime, and we've actually seen this reaction before, and it produces carbon dioxide in the process as well. So calcium carbonate thermally decomposes to form calcium oxide and carbon dioxide. And so another word for calcium oxide is actually lime. And so again, if they use lime in an examination, you have to just interpret that as calcium oxide. And so water can be added to calcium oxide to form calcium hydroxide. And this is actually called slaked lime. And you should be familiar with that as well. So calcium oxide added to water gives you calcium hydroxide. Note that in an aqueous solution of calcium hydroxide, we call that lime water. So calcium hydroxide itself, the solid form, is basically slaked lime. Now if you were to put that into water to produce a solution of calcium hydroxide, that is called lime water. And lime water goes milky in the presence of carbon dioxide. And take a look at this equation here. You get calcium hydroxide reacting with carbon dioxide. You produce calcium carbonate and water in the process, and the solution goes milky. So the uses of calcium compounds. Calcium oxide, or again lime, and calcium hydroxide are both used to treat acidic soils and neutralize acidic wastes because of their properties as bases. Calcium carbonate has fairly sort of various uses that we see here. First of all, the manufacture of cements, the manufacture of glasses, in a blast furnace, and in steel making to remove silicon oxide as slag, to neutralize acidic soils and lakes caused by acid rain. All these sort of stuff are things, if not more things, that you can come up with as uses of calcium carbonate. So that wasn't too long of a topic for either one of those, but it is still an important part of the syllabus. So I hope this video helped. Please visit www.freeexamacademy.com. I have written out basically the entire igcse chemistry syllabus. I will be moving on to physics very shortly, so check that out. Organic chemistry will come next in terms of video. So the next video I upload on YouTube will be on organic chemistry. I know that a lot of you guys have been requesting that, so it will be up very, very shortly. Also, if you guys haven't already, please join Patreon for exclusive past paper tutorials for both biology and chemistry. I've got 6 tutorials up for chemistry, and there will be more coming as well for that, along with resources, PowerPoint slides, and all that sort of stuff that I use for my YouTube videos. They will all become available to you if you join me on Patreon. Otherwise, please like, share, and subscribe my videos, guys, because the more likes, the more shares you guys have on my videos, it gets ranked higher on YouTube. That means it gets more exposed more to other students that might, that might gain aid from the videos I upload on YouTube. So basically, thanks for all your support, guys, and I will see you in the next video. Cheers. Hey guys, welcome to another igcse chemistry revision video. Today we're going to be going through 2 topics. We're going to be going through sulfur and also carbonate. So without further ado, have a quick look at the syllabus content. It's not a long topic for either of these, and we'll begin the video. So the sources of sulfur is found mainly in underground sulfur beds in the USA, Mexico, and Poland. Natural gas and petroleum contain a moderate amount of sulfur compounds. These have to be removed and are also an important source of sulfur. Metal sulfides occur as ores, and one example of this is a zinc blende, and you should know of this already in terms of the extraction of metals. And if you don't know that, you should go and revise that as well, because they tend to ask you a lot about that in exams. So when we take a look at sulfur dioxide, which is basically an oxide of sulfur, sulfur dioxide is mainly used in the contact process. And the contact process is a fancy word for the process that manufactures sulfuric acid. And you'll find sulfuric acid in a lot of different places, and there's a lot of different uses that we will be going through later on. But for the sake of your sort of experience and things like that, you would have found sulfuric acid widely spread in your laboratory rooms and things like that, and it is an example of a strong acid. Sulfur dioxide is also used in bleach, in the manufacture of paper from wood pulp, and as a preservative as well for killing bacteria in food. So we talked about sulfur dioxide being used in the contact process, which is the process that makes sulfur dioxide. So let's just go through the steps, because this is quite important, and if they're going to be asking you any sort of question about sulfur, generally it would be about the contact process. Sulfur is basically burnt in air to form sulfur dioxide. Simple. Sulfur plus oxygen gives you sulfur dioxide. This is then mixed with oxygen to form sulfur trioxide, and this is important here that this is in equilibrium. So we've got the double arrow suggesting that it's got the forward reaction and also the backward reaction as well. But either way, sulfur dioxide reacts with oxygen and you form sulfur trioxide as the product. So the reaction between sulfur trioxide and water inherently produces sulfuric acid. Unfortunately, this isn't exactly what we do in the contact process, despite the fact that it works, because this reaction between sulfur trioxide and water is very, very violent and explosive. And so you can't really do that to make sulfuric acid. Instead, what you do is basically add sulfur trioxide. You dissolve that or add it into sulfuric acid or concentrated sulfuric acid, and we produce something called oleum. So here's the reaction here. You got sulfur trioxide. Instead of just putting it straight into water, you put it into concentrated sulfuric acid, H2SO4, and what you get is this compound here, H2S2O7, which is oleum, and you do need to know that. And what you then do is add oleum to water, and that will give you 2 moles of sulfuric acid, as the last equation shows you here. So that's a roundabout way of doing things to make sulfuric acid, because the reaction between sulfur trioxide and water is way too explosive to carry out in this procedure. There's a couple of things that you need to know regarding this whole process and in terms of the conditions that is required, because they like to ask you that as well. So the conditions are 400 to 450 degrees Celsius. The pressures are between 1 to 2 atmospheres, and the catalyst that is used is vanadium 5 oxide. So the properties and uses of sulfuric acid. When we think about dilute sulfuric acid, despite the fact that it's dilute, it's still a very strong acid, and it'll show characteristics of typical strong acids. And of course, strong acids are acids that completely ionize in aqueous solution, and they have characteristic acid-like reactions, say with metals, with bases, and whatnot. The general uses of dilute sulfuric acid would be to make fertilizers, treat metals, and remove oxidation before painting. Laboratory reagents that you find in your labs at school, acid and car batteries, dye, fiber, and paint manufacture, all that sort of stuff are fairly common uses. When we talk about concentrated sulfuric acid, the properties, of course, would again be that it's a strong acid, it's a very powerful dehydrating agent, and it's a very powerful oxidizing agent as well. The uses would be similarly to make detergents. It can be used as a catalyst, and it can also be used as a dehydrating agent. As we talked about above, one of the properties are that it is a dehydrating agent. So moving on to carbonates, a lot of this is focused on calcium oxide. And so the manufacture of calcium oxide is something that we'll have to talk about. So let's actually get some terminologies sort of set first. So calcium carbonate, another word for that is limestone. So don't get confused if they use limestone in an exam, because it simply means calcium carbonate. Now, calcium carbonate or limestone decomposes into calcium oxide, which is lime, and we've actually seen this reaction before, and it produces carbon dioxide in the process as well. So calcium carbonate thermally decomposes to form calcium oxide and carbon dioxide. And so another word for calcium oxide is actually lime. And so again, if they use lime in an examination, you have to just interpret that as calcium oxide. And so water can be added to calcium oxide to form calcium hydroxide. And this is actually called slaked lime. And you should be familiar with that as well. So calcium oxide added to water gives you calcium hydroxide. Note that in an aqueous solution of calcium hydroxide, we call that lime water. So calcium hydroxide itself, the solid form, is basically slaked lime. Now, if you were to put that into water to produce a solution of calcium hydroxide, that is called lime water. And lime water goes milky in the presence of carbon dioxide. And take a look at this equation here. You get calcium hydroxide reacting with carbon dioxide. You produce calcium carbonate and water in the process, and the solution goes milky. So the uses of calcium compounds, calcium oxide, or again lime, and calcium hydroxide are both used to treat acidic soils and neutralize acidic wastes because of their properties as bases. Calcium carbonate has fairly sort of various uses that we see here. First of all, the manufacture of cements, the manufacture of glasses, in a blast furnace, and in steel making to remove silicon oxide as slag, to neutralize acidic soils and lakes caused by acid rain. All these sort of stuff are things, if not more things, that you can come up with as uses of calcium carbonate. So that wasn't too long of a topic for either one of those, but it is still an important part of the syllabus. So I hope this video helped. Please visit www.freeexamacademy.com. I have written out basically the entire igcse chemistry syllabus. I will be moving on to physics very shortly, so check that out. Organic chemistry will come next in terms of video. So the next video I upload on YouTube will be on organic chemistry. I know that a lot of you guys have been requesting that, so it will be up very, very shortly. Also, if you guys haven't already, please join Patreon for exclusive past paper tutorials for both biology and chemistry. I've got 6 tutorials up for chemistry, and there will be more coming as well for that, along with resources, PowerPoint slides, and all that sort of stuff that I use for my YouTube videos. They will all become available to you if you join me on Patreon. Otherwise, please like, share, and subscribe my videos, guys, because the more likes, the more shares you guys have on my videos, it gets ranked higher on YouTube. That means it gets more exposed more to other students that might, you know, that might gain aid from the videos I upload on YouTube. So basically, thanks for all your support, guys, and I will see you in the next video. Cheers.